In this video, we're going to solve a mole response spectrum analysis problem that is shown on the figure. We have rigid beams and flexible columns. Notice the flexible columns include a moment of inertia of 1400 inches to the fourth, a cross-sectional area of 50 inches square. The cross-sectional area is going to be important in developing the stiffness matrix, so we'll have to ensure that this is a reasonable cross-sectional area. We are solving first for the periods and the mode shapes, and then we will find the base shear by the square of the sum of the squares for a response spectrum found in Chopra figure 6.9.5. The steps in RISA are as follows. We will set parameters, both the description and solution parameters, followed by a consistent set of units. Then we'll modify the drawing grid consistent with the sketch. We'll create the model, both the area and material properties as well as the boundary conditions, and then we'll input appropriate loads, including the response spectrum. Finally, we'll input load combinations and perform a solution, which includes the dynamic solution to determine the periods and the mode shapes, followed by a static solution to determine the base shear. Once we get RISA started, we'll check the global parameters. This is an example. We will check the seismic. All the parameters here should be left as defaults. We will input the response spectrum as a separate file. And then what we do next is we ensure that the units are consistent with the units we have, which they are. And we finally go into modifying the grid. We'll use one space of 24 feet in the x direction and 3 spaces at 12 feet for the y direction. That will give us a grid like so. This point, then we go in and create our members. So we'll pull up this member, draw members menu. We're going to use a general shape. So it is a steel shape, so general steel. It's for the columns. We'll create a member using this shape selection. We'll add it. We're going to call this column. It will have an area of 50 square inches. We'll just use a moment of inertia along the y-axis of 1. This is 1400, and then this will be 1401, and I will change those to 1s because otherwise we won't get a result. We'll okay that, cancel, pull this up again, and there's my new shape. I will add it. Notice this went back to concrete, so I have to make sure it goes to steel columns, and we start drawing our members. So we have 3 columns on each side, and we also have rigid beams. So I will pull up the draw members tool again, and this time I'm going to assign a section that is rigid for the beams. I don't give us a very stiff beam. Apply. We'll create 3 beams, and there is our model. The next thing we need to do is add the boundary conditions. So we have fixed supports at the base. The other thing is this is a 2-dimensional problem. So as we discussed in previous videos, we have to make sure that these are fixed out of the plane of the model. And we have the 2 fixed supports. We have to go back and ensure that all the other joints stay in 2 dimensions. So I have to make sure that they're free to translate into the plane and rotate. And we'll simply add that boundary condition to each node. At this point, we need to do is put in loading. We have at the top, we're going to have a concentrated load of 50 kips, and it's going to be located at 12 feet, so right in the middle. We then do this again for the other 2 floors, but with 100 feet, with 100 kips. And then we have to include a response spectrum. We have to go to Modify, Response Spectrum Library, and in here there's a number of different response spectra that have already been inputted. The one we're going to use is Chopra figure 6.9.5. So when I edit this is the values that you have to put into this response spectrum, all the way down to, so I will put it there. You can put those values into RISA. You create a whole new response spectrum. So at 0.8, 0.75 to 0.25, and then the last from 0.2 to 0.005. So that's a response spectrum. Here's what it looks like as a single plot. So this is a spectrum that is in Chopra, figure 6.9.5. Once we have this response spectrum, we have to go and create load combinations. And our load combinations will include the response spectrum along the X, and also that is going to be factored by 0.25, and then also the response spectrum, not the response spectrum, but the other loading, the static loading. So we'll include that, and we'll use the full load. This was discussed in the previous video. And so there's my full model, my loading, and now what I have to do is do two different types of solutions: a dynamic solution, the eigen solution, and response spectra analysis. And so solve, and here we have different choices for combination methods. So we have the complete quadratic combination, the square root of the sum of the squares, and then also Gupta. So we're going to use the square root of the sum of the squares, x direction. We're going to use 5% damping, and so we'll have to go on the spectra. We have to go down until we find the Chopra figure 6.9.5, which you will have to input into your RISA program. And we start the solution. There's an error, so we'll check the load combinations. The load combinations appear to be okay. Oh, this should be 1, not dead load. So we'll put that as 1, and now we can solve the problem. These parameters don't change, so start the solution, and there's our period, 0.354. By comparison, this solution was performed using generalized single degree of freedom case and a multi-degree of freedom analysis. And here's what I got with the generalized single degree of freedom case: 0.3405. I get 0.348 with RISA. Multi-degree of freedom, I get 0.3418. The mode shape that was used in the generalized single degree of freedom is this phi. The eigenvectors from multi-degree of freedom are here. Here are the RISA results, very close. All the eigenvalues and eigenvectors, of course, they should be close. This, however, did not include the axial stiffness in the development of the stiffness matrix. So there should be some results a little different. Now, to go back to RISA, we can go and solve this a second time for a single load combination to get the static results. And now that we have solved for the static results, we can bring up the joint reactions. And notice the joint reactions, your total reaction is going to be 157 kips, which compares very well with both the generalized single degree of freedom case as well as the multi-degree of freedom case. I hope this was useful.